Dear students, in this video we will see an important theorem on cyclic groups. That is, we will prove that every subgroup of a cyclic group is cyclic, right? So before going to the actual proof, let us try to understand with an example, right? See this example. This is a well-known example. We have already worked it so many times. So G is a group with respect to multiplication 1 minus 1 I minus I. Do you know this is a cyclic group generated by I, right? Now H is equal to 1 minus 1. This is a subgroup of G, right? Now what is our aim? Our aim is to prove that every subgroup of cyclic group is cyclic. Therefore, what we wish to prove is this H is also a cyclic group. What do you mean by cyclic group? So H should be generated by some element. What is that element? That element should be from H only. Please remember, right? It should not be I, because I does not belongs to H. So see here, an observation is that G is generated by I. That means you will get every element of G when I is raised to some power. That is I power 1, I power 2, I power 3, I power 4, and continue this, you will get every element of G, right? And because H is part of G, so what is H? 1 minus 1. You should also get the elements of H when you raise I, okay, to different powers, different integer powers, right? Now, among them, see here, I when raised to 2 is minus 1 and I raise it to 4 is 1, okay? So these two elements forms H, isn't it? Now among them, what is the minimum power? 2, right? So that is why I have highlighted this. Now what we are going to prove is this H will be generated by this I square element. What is I square actually? Minus 1. So what I am going to prove is H, that is minus 1 and minus 1 will be generated by minus 1. Okay. So what is minus 1 power 1? 1 minus 1, and minus 1 square plus 1, minus 1 cube again minus 1. What is minus 1 to the power of 4 is 1. So therefore minus 1 generates every element of H. Therefore H is generated by a single element minus 1, and minus 1 is also belongs to H. Hence H is a cyclic. Do you understand? But this is an example. We have to give general proof, right? Similarly, you can also observe this example. Z6 is also a cyclic group. And here I have taken a subgroup of Z6, that is H, that is 0, 2, 4. Now, our statement is to prove that every subgroup of Z6 is also cyclic. Therefore, H should be generated by some element of H, not element of Z6. Of course, it should be, it will be an element of Z6, but that element should comes from H itself, not from outside H, right? We'll see. So now Z6 is generated by 1. How 1 generates Z6? Because the operation is addition modulo 6, we don't write a power n, but instead we write n dot a. N dot a means a plus a plus a plus so on n times. But here addition, in place of addition, the operation is addition modulo 6, because Z6 is a group with respect to addition modulo 6. So therefore 1.1 is 1, 2.1 is 1 addition modulo 6, 1 is 2, 3.1, 1 addition modulo 6, 1 addition modulo 6, 1 is equal to 3, and so on and so forth. See, using 1 you can get every element of Z6, hence Z6 is generated by 1. Now my question is, which element generates H? Okay, for that you observe, so what powers or what multiples of 1 gives rise to the elements of H? See here, 2.1, 4.1 and 6.1 forms the set H, that is G2, 4, 0, of course, in different order, but this is equal to H, right? Among them, you choose the minimum power or minimum n. What is the minimum n? 2. So what I will prove that H will be generated by this 2. See, 2. 1.2 is 2. 2.2 is what? 2 addition modulo 6 2 is 4. 3.2 is nothing but 2 addition modulo 6 2 addition modulo 6 2 is 6, but addition modulo means divide this with 6 and the remainder is 0. Therefore, see here, from 2 a single element 2 you can get every element of H. Therefore, H, that is 0 2 4, can be generated using a single element 2, hence H is also a cyclic group. Do you understand? Okay, this is the idea of the proof, okay, of the theorem. We will go to the proof now. Yes, now we will go to the original proof of the theorem. Now we want to prove every subgroup of a cyclic group is cyclic. So let us start with a cyclic group G, okay, and let us also take a subgroup, say H of G. Because H is a subgroup, H is a group by itself, right? So that means it satisfies all the four properties of group: closure, associative, identity, and inverse. Now what is our claim? H is also a cyclic group. Means what? H should be generated by some element, right? That is what our claim is. Now, so for that, first we have G is a cyclic group. Means what? Means what? So there exists an element of G such that it generates G. It generates G means what? A power integers gives every element of G. That means you take different powers of A, okay, they will constitute, or you will get every element of G from that powers. That is what I have written here. So every element in G can be written as some power of A, okay, where P is an integer, right? P can be anything, M, N, you can name like anything, but P is an integer, okay. So here, now, suppose X is an element of H, X is also belongs to G, because H is after all a subgroup. Means what? First it is a subset of G. So every element of H is an element of G. Therefore, so this X can be also written as some power of A, right? From 1, okay. So therefore X is also a power something. So that is what we have seen here also, right? So even the elements of H 1 minus 1 are also can be written as I square and I power 4. That is some powers of I, because I is the generator of main group. Here also A is the generator of main group G. Therefore every element of H also part of G. Therefore that X can be also written as some power of A. Among those powers, let us take the least smallest power, that is M. See, same thing we have done here. See, here I power 1, I power 2, I power 3, I power 4. But I power 1 is not an element of H. This does not belongs to H, right? But what belongs to H? I square belongs to H, I power 4 belongs to H. Among them, what is the least power? 2. So let us consider I square. That is what I have written here. M be the least positive integer. So M be the least positive integer such that A power M belongs to H. That means what? If you take any element I, any integer I less than M, A power I is not an element of H, because M is the smallest such that A power M belongs to H. A power I does not belongs to H. Okay, that is what I have written here. Now what I prove is, we want to prove H is a cyclic group. So we will prove that H will be generated by this A power M. Okay, that is what I have shown you here in the example. I proved that H is generated by I square, right? So I square is what? Minus 1. Similarly, here also A power M will be an element of H. So let us name this as B, okay, for simplicity. So now what we will prove is H is generated by B. Means what? You take any element of H, say X. Now this X can be written as B power something. What is B? B is nothing but A power M. So A power M power something. Okay, that is what you are going to prove. Now let us see how we will do that. Okay, now let us, okay, so I already explained this. So if X belongs to H, okay, what I will prove is that X is generated by B, okay, that is X is some power of B or some power of A power M. Let us start with X belongs to H. So X belongs to G, and G is generated by the element A, therefore X is some power of, okay, X is some power of A. That power I assume it to be P. Okay, I already written this by 1. Now, by division algorithm, so that means you divide this P, okay, with M. Okay, what is M? M is the least positive integer such that A power M belongs to H, that M. Okay, and suppose it divides Q times and remainder is R. Then by division algorithm means Bhagahara niyamam. So divisor into quotient plus remainder is equal to the dividend. So P is equal to MQ plus R. What is R? R is remainder. Suppose M completely divides this P, then remainder is 0. Otherwise the remainder is 1, 2 up to M minus 1. It cannot be M. It cannot be more than M, right? So therefore R can be 0 to M minus 1. That is, R is smaller than M. Please remember that. If possible, suppose that, okay. Now, what we will prove is R is 0. Okay, but we will prove this R is equal to 0 by method of contradiction. Let us assume that R not equal to 0. Then, if R not equal to 0, R can be 1, 2, so on, M minus 1, because R is not 0. Then R is a positive integer, but smaller than M. Please remember this. Now, what is X? See here, X is equal to A power P, and this X we have taken from H, therefore this belongs to H. And A power M belongs to H. We have already written this, right? M is the smallest positive integer such that A power M belongs to H, right? Therefore A power M belongs to H. Now what else? And we have that if A power M belongs to H and H is a subgroup, means what? Group by itself. Therefore, what happens? A power M to the power of Q also belongs to H. What is A power M whole to the power of Q? A power M dot A power M dot A power M Q times, right? Because A power M is A belongs to H, belongs to H, belongs to H. By closure law, this to the power of Q also belongs to H. So A power MQ belongs to H. If an element belongs to H and H is a group, therefore its inverse also belongs to H. That is, A power minus MQ belongs to H. Hope you understand this. Now, when A power minus MQ belongs to H, and we already have A power P belongs to H, see here, and now A power minus MQ belongs to H, by closure law in H, A power P dot A power minus MQ belongs to H. Right? That means A power P minus MQ belongs to H. Why we are doing this? Because A power P minus MQ is nothing but R, because P is MQ plus R, P minus MQ is R. Right? Therefore, A power R belongs to H. When A power R belongs to H, okay, this is a contradiction, because I already told that R is the smallest positive integer, okay, than M. But what we assumed, M is the least positive integer such that A power M belongs to H. అంటే M కంటే చిన్న ఎలిమెంట్, చిన్న ఇంటీజర్ వేస్తే A పవర్ లో అది does not belongs to H అవ్వాలి. But A power R belongs to H. So this is a contradiction. So therefore, our assumption is wrong. What is our assumption? R not equal to 0 is wrong. So what is that? R is equal to 0. R is equal to 0 means what? P is equal to MQ. That means when you divide P with M, it completely divides, remainder is 0. Therefore, X is equal to A power P is equal to now A power MQ. That means what? X is where? X is what? An element of H. Now, how I wrote it? A power of A power M. Right? What is A power M? B. So, therefore, any element of X in H can be generated by B. Therefore, H is generated by B, and hence H is a cyclic group generated by A power M. Therefore, every subgroup of a cyclic group is cyclic. Understand? Okay. Thank you.